So we can start, Matteo, with the second talk of Matteo about your course. So please.
Thank you. So thank you all again for being here. I hope that the level of the course is suitable for all of you. If you have some complaint, just tell me or write me. And today I will deal with the existence problem. So existence means finding solutions, and it means finding a reasonable class of solutions. So in the parabolic setting, there are a zoo of solutions that I will try to briefly describe just after the introduction of this lecture. And then we will see how to build a suitable class of solution, because it has to be good both for existence and uniqueness and for doing estimates. No? And the two things go into different directions. Sometimes it is easy to find like numerical solution or semi-group solution, but then there you cannot neither usually integrate by part or this kind of thing. So it's really tricky. So let me start with the resume of the equation. The equation is ut equal L of f of u. L is the Laplacian, f of u is u to the power m for now. We assume initial condition at 0 times 0 and zero boundary condition. Okay. So for now, the only example is the Laplacian, but I will do everything which is fractional Laplacian ready or non-local operator ready. I mean, the property of L, the properties of L. Now for listening to the class, think of the Laplacian, so you know that you can integrate by part and do all the operations, and I will specify where really the structure of the operator enters, and in the class of today, we just need a monotone operator, and I will explain you what it is. Okay, so, but now let me do an overview of the course by explaining you what happens with the classical porous medium equation for the Dirichlet problem. It's like seeing the movie of the life of the solution from the initial data until the asymptotic behavior, and I will emphasize some key moments in which you really have to see that something happens. Okay, so it's like a slow motion movie of what happens to solution to this problem. And I think that with the class of yesterday was intended to make the people, I'm thinking more the students, but maybe also people who is not familiar with the porous medium equation, to understand what I'm going to say now. Okay, so let me put it full screen. Yes, so everybody can read, right? So bounded domain. Take a compactly supported initial data. This is not the problem. I mean, already with this data, you see the whole difficulty of the problem. So you take the porous medium equation on a bounded domain, zero boundary condition, and initial data U0, which we say is compactly supported and non-negative. Huh? There are a lot of work by all these authors. And of course, I forgot somebody, and I apologize for that. If you look at the book of Juan Luis, there are 300 references. So either I make a slides only with the names, or I will forget somebody. So let's see what happens at the initial times. At the initial times, if the semi-group, or if the parabolic equation is somehow decent, there is some kind of continuity. So at the initial times, the equation still remembers about the initial data. You see, there is the initial data, which can be these compactly supported, and for initial times, what happens that since there is finite speed of propagation, the equation forgets that it is on a domain. So it starts to behave like the fundamental solution on the whole space. And this is why yesterday I explained you something about the Barenblatt solution. The Barenblatt solution is compactly supported, it has finite speed of propagation, and if I have to write what happens in the first moments is this. You start from the initial data, you see this U0, and then you regularize, so you become round like the Barenblatt solution. What is the problem here? The problem is not nothing. You see, you have compactly support, and the support spreads exactly at this speed, as I explained yesterday. But what happens at the boundary of the support? At the boundary of the support, solutions behave like this, like the distance to the boundary to this power. And if m is big, you see this power is less than 1. So there is no way this function is twice differentiable. And here it is, this is one of the motivation of the theory of weak solutions, because also the fundamental solution to the porous medium equation, even if you start from the nicest initial data, is not classical. That's it. There is a free boundary that moves, which is the support, the boundary of the support. It expands, and here the tangent is vertical, so you are just C alpha, and with this precise alpha. Okay? When M is small in the sense it's close to 1, is bigger but close to 1, yeah, then this can be Lipschitz at least. But it's never twice. I mean, when M is bigger or equal than 2, there is no way you get classical solutions. Okay, just wanted to mention this. And then, so for initial times, there is this Barenblatt behavior. So you expand like as if you are on the whole space. So what happens? At some point, you will hit the boundary, right? I mean, you continue to expand, you continue to expand. At some point here, you will hit the boundary. You see, you will hit the boundary of the domain here. And then there is a transition. A transition in what? What is that changes? Finite speed of propagation doesn't change. Solutions are just positive now. You see, they touch and they, but here there is a transition from what I called the parabolic behavior to the elliptic behavior. So here the solution somehow inflates. So you pass from the distance to this power to the distance to this power, and these two powers are ordered. So it inflates more. You see, you pass from a lower behavior to an upper behavior. It's not differentiable again, but it is different. And this is what we call the elliptic behavior. You will understand in a while why. Because the solution, the stationary solution to this problem, if you did the exercise yesterday, then you discover the solution of Laplace U to the M equal U, they have this behavior at the boundary. This is 1 over M is P. And remember that we were doing U to the P, and this is just saying that the solution of the semilinear elliptic equation with the concave nonlinearity behaves like distance function, and this is well known, okay? So, but at the beginning, the solution of the parabolic behaves differently, okay? So this is the first touching point. I mean, when it touches the boundary, the solution inflates. Then you wait a while, okay, then let me just say something about regularity. The solution are smooth and positive and as smooth and bounded whenever positive. But when they are 0, there is a free boundary, and the regularity of the free boundary is really a difficult thing. There are the pioneering result of Caffarelli, Vasquez, Volansky, and then later results now of 2 years ago by Kinsler, Koch, and Vasquez. But it's really delicate to study this, and we will not touch this problem in this course. But then you wait a bit, that the solution invades, becomes positive on all the domains. So after it touches the boundary the first time, it starts to touch the boundary everywhere. And there is a time, let's say T star, this phase, I call it reaching the boundary. So you arrive at the boundary uniformly at some point. No, you are invading the whole domain. No? And then, of course, you at the boundary inherits the elliptic behavior. So you get this boundary behavior. Good. And then what happens? Then it happens that we enter in the intermediate or large time interval. So it's where you start to behave like the asymptotic profile. You forget the initial mass, you forget the initial data, and you start to behave like the asymptotic profile. You can prove a global Arnaud principle, which means that you can bound U precisely from above and from below by 2 constants, independent of U, of course, and these two, the distance to the power, the distance to this power and the time to this power, which means that you are behaving like the solution of separation of variables for large times. And these 2 constants are independent on the initial data. So at this point, you completely forgot about the initial data and you enter the asymptotic regime, which in the case of the porous medium equation is very strong because really it forgets about the initial data. These 2 constants does not depend. And then what can you do more? Well,
sorry, Matteo.
Yes.
Matteo, sorry. And T star does it depend on the initial data?
Yes. The only point at which you remember, we will see this in detail in the next classes, but just a preview of what is going to happen. But yes, that's a good point. The T star depends is basically the time that it takes to be positive everywhere. It will eventually happen, and these can be estimated is basically T star is proportional to the L1 norm of the initial data. Well, more precisely, weighted L1 norm of the initial data.
Okay.
So this is the only point. I mean, the initial data only tells you how much you have to wait, but
Okay.
you will enter the asymptotic behavior and you will forget about the initial data at some point. So
Okay.
the influence of the initial data is just delaying or anticipating this T star. Okay?
Okay, thank you.
Thank you for the question. It's an important point indeed. Thank you. And so what can you say more? Once you are trapped between two solutions of separation of variable, can you say more? Well, you can say that, okay, you see clearly the association to the rescaled, to the elliptic problem through this. You know from the elliptic problem, what I was saying before, that S is behaving exactly as this concave power of the distance, okay, the stationary solution. And this is exactly what I wanted to tell you before. This is well-known, say, elliptic theory, but this is the elliptic connection, which is very strong in this case. And then what do you say? Well, you want to understand what does this mean? I mean, both U and S are going to 0, so what does it mean that they are similar? Well, it means this inequality, but can we say a bit more? Well, you have to rescale variables, and what you can prove is that the rescale solution, so the solution for which really the elliptic equation is stationary, it solves Vt equals 0. Then you converge uniformly to this solution. So in L infinity. But you can say even more. You can say that these two constants, C1, C0 and C1, asymptotically tend to 1, which means that the ratio or the relative error goes to 0 with a certain rate. We can also say that this decays like e to the minus t in rescale variable, which amounts in original variable to this rate, C1 over 1 plus t, which, by the way, is optimal because if you take two solutions by separation of variables, this is exactly an identity. Okay, so, and this is, I mean, everything you can say. So let me summarize a bit with the graph. No, you start from the initial datum, then you enter the blue phase, which is when you resemble to the Barenblatt. And then when you start to touch the boundary, you become red, like elliptic. Okay? And that's pretty much all about what you want to describe. And then you want to make this thing quantitative, so you need pointwise estimate or uniform estimate or the strongest estimate you can get. And so you've seen the role of the solution by separation of variable, and what we can say is this, that you have convergence in relative error and with a rate which is optimal. This result was first proved by Aronson and Pelletier by PDE methods, sub and super solution, and a careful analysis. And there is this nice survey / there are some new things here by Vasquez of 2003, and then we applied this to a more general setting in a series of papers that I'm describing right now. This paper of Juan Luis is really nice because it's a bit of survey, so it really explains very well the problem and the technique, the state of the art at that time, 2003, of the porous medium equation. Okay, so this is what I want to try to describe in this course, and of course we will not be able to do the whole theory. The regularity will leave it a bit outside because it's the eigenregularity, saying the solutions are once positive they are C alpha, and then classical or even C infinity when the operator allows it. This is a bit too technical for this course, but it's true. So today, I would like to concentrate on the abstract parabolic problem. Okay, so the abstract parabolic problem, it means we want to solve this problem. Okay, and for a general operator L and say a general nonlinearity f of u, it really doesn't matter. But in order to not make confusion for now, use always f of u equal to u to the m. Okay, it will work under reasonable assumptions that are written in the next slides, but now I want really to explain to you a couple of ideas, a couple of yeah, key ideas to solve this kind of problem in a reasonable way, let's say, to find a good class of solutions. Okay, so let me now switch to the blackboard, and then we will see which are the main theorem and how to build solutions here. So let me switch to the blackboard, and now we start about classes of solution. Solutions. I will be brief with this, just recall, but I wanted to explain a bit the key idea. No? Well, first there is the concept of classical solution. Classical solution, what does it mean? Well, first we have to specify the equation, right? This is the abstract way of writing it, and this is what you want to think about. Okay, classical solution means that this equation is satisfied in the sense of continuous functions. So solutions have to be C2 in space and C1 in time. It is always better to add an alpha here because you want to make sure there is always a bit of margin, no? Even if it's not strictly necessary. This is what I mean by classical solution. Of course, classical solution can be more regular, can be smooth. And smooth, it means C infinity in space and time. But even you can then go deeper, analytic, oops, sorry. They can even be analytic or ultra analytic, Givray, etc. We will not see this. But at least up to here, if you read my paper with Alessio and Xavi Rosoton, we arrive in one case to this regularity, and we estimate also the blow up at the boundary. So, but this is, okay, classical solution. We have seen that in the case of the Laplacian, there is already a problem because the fundamental solution is not a classical solution everywhere, only where it's positive. So then you need weak solution. What does it mean, weak solution? It means that they satisfy a weak formulation. Here I mean integrate between in time and in space. And here you integrate by parts. So you pass the time derivative to the test function, and you pass one derivative to the test function, one derivative in space to the test function. Okay, here I'm integrating in the x dt, etc., etc. Okay, so here basically the weak solutions are the one in which you only need one derivative well defined. Often we require that the energy is finite, so you require um in H1, so it means L2 with derivative in L2, no? And this is a good class of solution. Then there is the strong solution. What are the strong solutions? Are weak plus the time derivative is a function. L1, say at least L1 log, but usually it is better to ask for L1, etc., etc. Why this class of solution is nice? Yeah, because here we can derive norms and make computation. But the class of strong solution basically is good because you have contractivity and comparison. Okay, so these are the main classes. And then, unfortunately, the easy to construct solution are the mild solution, which is something in between the weak and the strong. And this, I will devote the rest of the class to explain what they are. So let me skip just this. But they are called mild or semi-group solution, just because they are in between the weak and the strong solution. They are weak solution, but they are not strong in this sense, always. And then there is the very weak solution. Very weak solution is when, well, in time there is not much you can do. But in space, you can also integrate once against by part. So you have this. Why the very weak solution and opposite to distributional solution? What is the difference? Well, in the formula, there is no difference. Sorry. In the formula, there is no difference. You integrate twice by part. You apply, if you want, a distributional derivative. But here, you ask that u or u to the m is in L1 log. Here, you don't. You just ask that u to the m is in d prime, and u also. Okay? So, and this is
Excuse me, Matteo, is this Laplacian of U in the second integrals in the two lines? Laplacian of okay.
Probably Laplacian phi.
Yes.
Okay.
Sorry.
Okay,
yes.
Thank you.
Yes. So, so here we ask that these are functions. Here, usually you ask that they are merely distribution, but indeed they will be measures because you are considering, I did not say it, but let's restrict our discussion to U greater or equal than 0. So here distribution with the sign are measures. So here you are not that far from functions. Huh? We are in the tier of measure. And then there are here some solution in H minus S, or if you prefer, in the case of the Laplacian, in H minus 1, which is a space I will call like H star. And there is this very weak theory of solution in this space, which is what I will talk about a bit today. And this is an idea of Bresis. And these are very weak solutions, and it is a nice class of solution to build other solutions. So the idea is we have this zoo of solutions. So you have classical, and then you have weak, and then you have strong here, and then you have very weak, and then the whole blackboard is distribution. Okay, very weak, and then you can separate like this by saying these are the one with energy finite and these are the one without energy finite. You can always specify weak and strong energy, mild and strong energy, and so on. So there is this zoo of solution. So which is the right class? Or not the right, but the most convenient. There is not a right class. Okay? You always hope to end up with classical solutions, right? So what do we do? So the basic idea here is to start to understand the concept of gradient flow. What is a gradient flow? How do we interpret the equation, etc., etc. So let me start with a bit of, say, gradient flows ideas. Because it was very difficult at the beginning to me to understand in which sense the gradient flow are solutions. Okay? The idea of the gradient flow. The idea of the gradient flow is the following. You have an equation like ut equal minus L of u to the m. But even in the simplest case, m equal 1 is already, the idea is already there. So there is, well, the idea of the gradient flow is to think that this operator L is the variation of some energy. The variation in the sense of standard calculus of variation, what Gianmaria was talking about before, okay? So, and in which sense? So let's start from the simplest example. We take the heat equation, and we take the following energy, which is, I mean, I'm not saying anything new, so it's just to recall you something that you should remember. You take the quadratic energy, and what do? You do the variation in the point u in the direction phi. And this is the limit as h tends to 0 of E of u plus h phi minus E of u divided by h, right? And if you do the computation, exercise for the younger, you arrive to this formulation, gradient u, gradient phi, nothing new so far. And this, we would like to see it integrating by part in this way as minus Laplace of u phi. And this is L of u, okay? But if you think about it, what we found is L of u, comma phi, scalar product in L2. So this is the variation with respect to the L2 norm or at L2 topology, okay? So what does it mean to be a gradient flow? It means that your equation somehow follows the steepest descent or the gradient of an energy which you hope to be convex. Okay, this one is convex. So what are the derivative of convex function? Monotone object. In particular, if you take minus a convex, they are decreasing. No? And in this sense, our operator are monotone. So they are derivative of convex stuff minus the derivative of convex stuff. So they go down. Okay, they try to minimize at every step. the thing. So in which sense this equation is satisfied or can be seen as a gradient flow? Well, since here you want to solve this equation, well, a good idea would be to say, okay, you impose that this is equal to minus ut of phi in L2. And so what does it mean to satisfy the equation? It means that ut plus L of u to the m is equal to 0 in L2. So it's 0 almost everywhere as an L2 function. Okay, so the equation needs to be satisfied everywhere. Ut has to be a function. And in this sense, you are a gradient flow solution. Okay, so how do you see the connection between the heat equation and the energy? Well, it's quite simple. You derive in time the norm with respect to whom you, with respect to which you are taking the gradient of the energy. So you take the 1/2 the integral of u squared, and let's derive it along the flow. This is just u ut, and what do you get is the equation. You get Laplace u comma u, you integrate once by part, and you get minus integral gradient u squared, which is minus the energy. And this is the computation that tells you, that shows you, I will give you in a while more details, but this is the computation that tells you that the heat equation is a gradient flow, that this equation is a gradient flow with respect to this energy and this topology, the topology given by the L2 structure. Okay, I don't know if this is clear enough, but I will explain you how these allow to generate solution. Basically, what you do, the basic idea is you take this equation for existence, the basic idea behind gradient flow. The basic idea is what it is called ETD, implicit time discretization scheme, which is you discretize the derivative in time. So you write u t plus h minus u of t divided by h, and you want it to be equal to minus ut plus h to the power m. Okay, so you rewrite these in the following way. So ut plus h plus hl of u t plus h to the power m equal ut. So what are we trying to solve here now is, this is an elliptic equation, is the identity minus h the operator, plus h the operator, sorry. And this is right hand side, is an f. Okay? And this is where this computation really enters, because this computation tells you that you can all, well, the assumption on the operator, the fact that this operator is the derivative of a convex function tells you that you basically always can solve this problem for every f in this case, L2. You want to solve here, for example, here the setting is u0 in L2. Can I find a solution u of t in L2? The answer is yes, because you can solve this elliptic equation in L2 easily. And then you have to pass to the limit. Be careful, this is the implicit Euler scheme. It's not difficult to state, but then to pass to the limit here, you need, well, the finest analysts of the last century, some of them, Bresis, Crandall, Pazzi, the guys who invented nonlinear semigroup theory or built up Benilan, etc., etc. Okay, so this is simple to understand how you solve this equation. It's discretizing and passing to the limit, but then doing the details can be messy, and it's difficult analysis, functional analysis techniques. But essentially, you want to make this numerical scheme converge. There is a very nice paper of Nochet and Savare about this, in which they explain this setting. Here we are in Hilbert spaces. What happened in Banach spaces is slightly more complicated, but basically the idea is to replace the scalar product with the duality product. And it is more work, of course. The theory is quite complicated. So, but let me just, how much time do I have left?
You have 15 minutes.
15, okay.
15.
So let me just make another computation which explains a bit more the setting, okay? If you want to do things now in H-1, what is H-1? Well, H-1 is the dual of the subgroup space H10. Okay, but for me and for all our purposes, just think it as a space of distributions, whatever it is, such that the following quantity is finite. You want f L minus 1 of f to be finite. And this is, if you want, L minus 1/2 f squared. Okay? What is L minus 1? L minus 1 is a short notation for minus Laplacian minus 1. Well, the inverse of the operator we are dealing with. The inverse of the positive operator. This is a quadratic integral, which is the dual of the square of the gradient. Okay? Or if you want the square of the gradient, you can always also the h1 of omega. What is it? It's the f in L2, such that the integral of f minus Laplace f is finite. And then this we like to call it gradient square, but it is what it is. So this is equal to the integral of gradient f square. So why this space is so nice? Well, this space is so nice because it allows to do the gradient flow trick with this energy. So you take now this energy, which is 1 over m plus 1 integral of u 1 plus m. And it is convex and so on. And you want to make the variation of this energy with respect to the h minus 1 topology. So the trick that we did before is not so clear. But what happens if you make the variation of this energy of u in the direction phi with the h minus 1 topology? Well, exercise for you. You will end up with u against phi. And you can say, oh, how do I see, u to the m against phi? How do you see the structure here? How do I see that there is? Well, it's quite easy to see because here you can always multiply by L minus 1. I mean, you can make it appear here. This is the identity, right? And then you can, well, it is better to make it appear in front of you, sorry. And then what you get, and then you can always, since this is just the integral against the green function, it's a smooth thing, you can just Fubini it. You can pass it to the other side. So this is L minus 1 L of u to the m phi, but then you can pass this here just by Fubini, just as interchanging the order of integration. And what you get is L of u to the m L minus 1 of phi. And now this is a scalar product in h minus 1 because you have a function f times L minus 1, a function phi. So this is exactly L of u to the m, comma, phi, the product in h minus 1. And here there is the structure. You see, you kill the Laplacian, so you can allow for less regularity than the u to construct your solution. And this is an old idea of Bressis, but I thought it was brilliant because basically the idea is not to study this equation, for which in the best of the cases, well, u is a measure, and it always gives you problem. You cannot derive norms, you cannot do many of the computation you don't want to do directly, you have to approximate, and it makes all the things, life more complicated. But then the idea, which was used by Pierre to prove uniqueness, for example, for this problem, is to apply L minus 1 to both members. So you pass to what we call the dual equation, which is L minus 1 of ut equal minus u to the m. And now, even if ut was a measure, the potential of a measure is a function. Well, exactly it has the same regularity you ask for u. So at least it's L1 or L2, depending on what you are asking now. Okay? So this is an advantage when you want to do computation. And this is a very nice way of looking at things. The dual, to have the dual perspective, okay? And what happens now with the variation of these? Well, once you did the variation of these, what you are trying to solve is exactly this equal minus dt of u, comma phi in h minus 1, right? This is the game. And how you are solving the equation? Well, point-wise, I mean, the equation has to be 0 in the h minus 1 sense. So in some distributional sense, if you want, okay? So this concept of solution is a bit weaker than the other one, than the L2 one. But easier to deal with. Then, whenever you have this setup, so you have a convex functional and an Hilbert space, then you can build the gradient flow and solve your solution. I will show you the precise theorem in the slides at the end. But once with existence that you can believe me that, okay, the Euler scheme, the implicit Euler scheme converges. I mean, you can believe that. The point is, where do I get the uniqueness from? And how do I check if I can use these powerful theorems? Well, in this case, there is what is called an EVI, evolutional variational inequality, which is like a practical condition in order to make sure that you can apply the Bresis-Komura theory. This is Bresis-Komura theory. Okay, and I write a slide with all the references and where you can learn it and so on. A couple of slides. And so here there is a practical condition, but the last computation I wanted to do today is to tell you how do I get uniqueness. Well, uniqueness depends on contractivity. So uniqueness depends or is strictly related to contractivity. What is contractivity? Well, contractivity basically is saying that the distance in the natural space is not expanding. So that the norm of u of t minus v of t given to solution, say in L1 or in h minus 1, or there are no other spaces for the porous medium. Well, there are no other normal spaces so far, but this is less or equal than constant 1. Here you really need 1, is 0 minus v0. So the distance in L1 or in h minus 1 or in some spaces is not expansive. How do you prove this? Well, look, there are two ideas basically. There is the L1 setting, which is Benilan, Crandall, Pierre, and many others, but these are the fundamental author, the author who did the fundamental contribution. In their one setting, you can prove this by doing the following trick. I'm doing a formal computation, then you have to justify it. But what you want to derive is basically this, u of t minus v of t. So let's write what is the equation for the difference. This is minus L of u to the m minus v to the m, and that's it, okay? And if you apply L minus 1, the obvious thing. So this is what? If we can do this is the sign of u minus v, and then there is a minus L of u to the m minus v to the m. But then here there is a nice trick. There is a nice trick which tells you, okay, the sign of u minus v is equal to the sign of u to the m minus v to the m. Why? Because the function power to the power m is increasing. So these are clearly equal. And now you have to observe what is known by Kato inequality. What is the Kato inequality? Well, it's the generalization to this continuous function of the following fact, that when you take, for example, the Laplacian of a convex function, what you get phi prime Laplace of u plus phi second gradient u square. But this is a sign if phi is convex. And so Kato inequality tells you that you always have these for every convex function and when the Laplacian has a minimum of regularity. And this is what is behind the theory of the so-called maximal monotone operators. So when you have an increasing function here, the Laplacian of the same argument, this needs to have a sign. So this we know is greater or equal than 0, hence this is less or equal than 0. And what does this tell you? Well, you integrate between 0 and t, you get this. Of course, this proof is formal, but it can be made rigorous by integrating at the beginning. Here, if you integrate in time something which is a sign, it still keeps the sign, and that's it. You can make it rigorous in 2 lines. The only difficult point is to derive the absolute value. And here you need that the Laplacian as a sign, is a function. So here you need to work with strong solution. Or you have to make sure that at least ut is a function. Here, there is a technical point where you really need a bit of tools. So you need to approximate the absolute value, etc., etc. There is like 2 or 3 possible ways to prove this. But then let me show you the idea of Brazis, which is even cleaner, in my opinion, which is the h-1 strategy. So you want to prove the same with h-1 here. So what do? You derive the h-1 norm, no? U minus v, L minus 1, U minus v. You integrate. Well, this is 2 times because you can eat, since this is symmetric, you can make the derivative eat only here or here, as you prefer. Let's make it eat on the first component. So you have ut minus vt, L minus 1, U minus v. Then you use the equation. Well, the equation was written just here. And so this is equal to minus 2, the integral of L of u to the m minus Vm, and then L minus 1, U minus v. But then, you can simplify. I mean, Fubini, again. You don't even have it to integrate by part, you just use Fubini, okay? And here you got minus 2 u to the m minus v to the m, u minus v integrated. And this is without cut or without nothing, is negative because it's trivial to check, okay? So, and this is the wonderful Brazis computation. I really like it very much, okay? And it gives you contractivity in h-1 norm in a quite natural way. And this is rigorous, by the way. I mean, here, if you pay attention, you can immediately put L minus 1 here, or if you want, you can make the derivative, time derivative, it here. L minus 1 of the time derivative is a function. And so here you're just working with function and everything is perfectly justified, and it's almost rigorous, this proof. You know, I mean, to make it rigorous, I leave it as an exercise to you, but it's really not that far from being rigorous. While the other one requires several other approximation and to be really careful. Okay, then as an exercise for tomorrow, try to repeat the same and try to prove the same inequality, but with the absolute value, with the absolute value replaced by the positive part. So, can you prove this? That this is less or equal than the integral of u0 minus v0 positive part. What is this? This is called in abstract semigroup books T-contraction. T-contraction means that it is a contraction, but it is a bit more because this actually implies the above. Because once you do it for the positive part, you do it for the negative part, which is again the same thing, and you get the result above. But this tells you a comparison, because suppose that u0 is less than v0, then this is 0. But also this is 0. So it implies that ut is less or equal than vt. And this is the simplest way I know to prove comparison. Of course, this you can do it in the, say L1 setting, but also here, you can derive, you can put a plus here, and everything is still true. Okay? So do it as an exercise. Prove comparison by doing this. And this is the easiest proof that I know. Huh? I mean, then you have to, okay, justify the approximation and whatever, but I wanted to show you where the positivity enters, where the maximal monotonicity, which means basically that the integral of, say, a convex function of u, an increasing function of u, or a maximal monotone graph of u times L of u as a sign. And this is the maximal, the monotonicity of the operator written in an integral way, or practically what you use in the computation. And this allows you to get a unique solution in these spaces. Okay, so this was more or less everything I wanted to say to the blackboard. Let me just, if I have still 5 minutes, I wanted to show you just the summary in the slides of what I've done, and then I will give you the slides. So look, I will talk a bit tomorrow about the concept of weak dual solution, but basically it's a weak solution for the dual equation. The dual equation, we already have seen what it is. It is exactly this. It is applying L-1 to both members or starting this. And by the way, the boundary conditions are already included here, because L-1 contains the fact that the solution that you are looking for are already zero at the boundary. So it's also smart in the, when you do computation, you don't have to care about many things. And then you basically write the definition of weak solution for the dual equation. So you multiply by a test function, which is allowed to be in L infinity and zero at the boundary with a certain rate, and that's it. So this is the H-1 setup that I was telling you before, and these are some references that you can read, some classical and some very news. And look, this is the theorem of the Bresisco-Mura theorem, say the contractivity in H-1, the contraction or the comparison, and the energy computation. And a nice thing is that all the theory in H-1 can be checked by checking what is called evolutional variational inequality, which is this. You derive the H-1 norm squared, and if this is of u minus an element, and if this inequality holds, then this theorem holds in its full generality. So you have in this case, it happens to be strong solution in H-1, which satisfies comparison, etc., etc. Okay, and then that's it. I mean, you have solution, and you just have to check this, which amounts to use Fubini, the dual equation, and Young inequality. So in order to apply this theorem is really, really easy. So this is a very powerful theorem. Then you have the L1 setup. I will skip. I put it in a slightly more generality by telling you that you can also treat more general things than powers. And this is the theorem of Benilan, of Crandall and Pierre, and it's contained in these papers and so on. And this is the reminder about the Euler scheme, and that's how we prove existence of weak dual solution. How do you approximate solution, weak dual solution with these classes of solutions? So let me just, sorry, I just wanted to finish with this idea. How do you build solutions to this problem? Well, first, you define a good class of solution, of, let's say, approximating solution. Once you have these, which can be the L1 solution or the H-1 solutions, then now we want to work the weak dual solution work well in this weighted space. And psi is L-1 of phi greater or equal than 0, a smooth function, say. The idea here is that we will take the first eigenfunction of the operator. So this is a classical space, but this is the game that allows you to get all the estimates. Okay, it's not important it is the eigenfunction, but it is the L-1 of a compactly supported positive function, or say a decent function, non-negative and regular. So how do you approximate function in this space? By means of this. Well, the simplest thing is to take a sequence U0n of solution, which is like this, maximum between n and U0. You truncate. You take your U0 in L1 psi greater or equal than 0. You take the truncates, they monotonically converge in L1 psi to U0, of course. And, and what happened? Well, each of these has a very good solution obtained by L1 or H-1 theory. So, and this is less or equal by comparison of this one, because all of these are ordered and they are monotonically converging to something. So this has a monotone limit because time, if you fix t and x, it is monotone in n. So by monotonicity, there exists a limit, which is ut. So if you're careful enough, and here you take the limit, so you obtain what we call the minimal solution, weak dual solution, then this solution is obtained by an approximation by a monotone sequence of very good solution. It inherits basically all the properties that you need. And this is how you build solutions. And this is the concept of sola, which I don't like because in Roman it means that you're being somehow cheated, or limit solution. Limit solution. So you work in good classes of solution, but in these classes of solution, maybe you cannot integrate by part, but here, yes. Well, it exists because it's a limit of monotone sequence of solutions, and that's it. Okay, so this is how you build solution and how you make sure that they are unique. Also, uniqueness passed to the limit somehow. And this is everything I wanted to tell you today. I hope you enjoyed the class, and I want to make an advertisement for the session. I thought after classes tomorrow or Thursday, it would be nice, who is interested to join